Hello, y'all. Welcome to Lesson 8, where we'll cover Structure 1.3.2 of the DP curriculum, DP Chemistry curriculum. Today, we're covering the line emission spectrum of hydrogen, how it provides the existence for electrons in discrete energy levels, which converge at higher energies. By the end of this, we should be able to describe the emission spectrum of the hydrogen atom, including the relationship between the lines and energy transitions to the first, second, and third energy levels. You will not need to know the names of these spectrums, and we'll cover that in a moment as we get there. So, we learned about the emission spectra of atoms and elements in our previous lesson. Today, we're focusing on hydrogen, um, as first worked on, I believe, by Niels Bohr, who gave us our Bohr model. But why hydrogen? Well, hydrogen itself is the simplest element, is the simplest atom. A hydrogen atom has one proton and one electron. And because of that, there's not a lot of interference from other particles. We know that everything that happens is a relation of just one positive and one negative charge interacting with one another. So, what this does is it will allow us to effectively model the absorption and emission of light due to electron transmissions or transition, sorry. So as our electron transitions from different energy levels, we can model how light either interacts with that electron being absorbed or released. So we're going to actually use a diagram here where we'll diagram specifically the energy of each energy level, and we'll make our energy levels here starting with n equals 1. We're gonna go all the way to n equals 6 about. And something you'll notice is the spacing between the energy levels gets smaller and smaller. They are converging. Sorry, this one's throwing me off here. One, two, three, four, five, and one more. So as we go through our energy levels, they converge at the higher energies. 3, n equals 4, n equals 5, and n equals 6. We're using n, the principal quantum number, to describe these energy levels, and n equals 1 is our ground state. Now, the first thing that we do have to know is any electrons that transition from 3, 4, 5, or 6, and they fall to n equals 2. Once again, I seem to not have the complete right colors. These produce visible light. So we get light in the visible spectrum here. So these transitions will always produce a visible light wave. And this tells us something else. We notice that there are specifically one, two, three, four lines in our emission spectra. We saw that in our previous experiment or demo or example where we looked at the emission spectra, the line spectra of hydrogen, we see four discrete lines. This is really important. This tells us that this is proof that electrons can, can only exist in discrete energy levels. Because we're never going to get an orange line by a transition that starts midway between 2 and 3 or any lines that start midway. We only get lines that represent discrete transitions from one energy level to another. These, however, only cover visible light. So we can actually take this entire diagram, which I will try and copy effectively, and I'll bring it down to a new page, and we'll get rid of these lines. Actually, instead of just getting rid of them, we'll move them. All right. So we have our visible light transitions, but you might be asking, well, what happens if we have something that goes to n equals 1? Well, that can happen too. So we can have these transitions that go all the way to n equals 1. So we can do n equals 2 to n equals 1, n equals 3, 4, 5, even 6. So these transitions that go to n equal 1 all produce ultraviolet light, which we can't visually see so that we don't get it in our line emission spectra. So we're still going to get discrete wavelengths of ultraviolet light, having this being the lowest energy ultraviolet and this being the highest energy ultraviolet, just like red was our lowest energy visible and violet was our highest energy visible. But because they're UV, we will not be able to see them. We can actually continue this even further, trying to not maintain the ultraviolet. So we can also have transitions that don't go to n equals 2, but instead go to n equal 3. So 4 to 3, 5 to 3, and 6 to 3. And these transitions are actually infrared. And much like ultraviolet, this is low energy infrared, and this is high energy infrared. However, high energy infrared is still less energy than low energy visible. So hydrogen actually has a bunch of different frequencies and wavelengths of light that can be produced from its energy levels. We just can't see any of them but the four visible lines. The last piece of this lesson is that we notice that these energy levels converge at high energies. We see that here as we go up to 4, 5, and 6, the spacing gets smaller, less space between n equals 5 and 6 than n equals 1 and 2, so that space reduces. And we actually have an energy level called n equals infinity. And this is basically the point where they all converge up here, just past 6. And at n equals infinity, we basically say electrons have effectively left the atom. So if it goes past n equals infinity, the electron is gone. So with that, that's the end of the lesson. Hopefully this helps. Have a great day.